Okay, why don't we go ahead and get started? We may still have folks joining in, but we've got a lot of content here, so don't want to keep you all waiting any longer. Folks will just have to catch up when they do join. Thank you all for joining here. We have the next 60 minutes to talk about our distributed wind energy futures study. We're going to talk a little bit about the background for the study, what we were seeking to achieve, a little bit of touching on the methods, so you understand kind of the analysis that was completed. We're going to spend most of our time talking about some of the key results and figures that are also available in the full report if you've had a chance to look at that. We'll wrap up with some discussion around the intersections with energy equity and basic conclusions. So that's the lay of the land for today. We have a variety of the authors from the team that are going to be able to present their different portions of the analysis. So you'll get to hear from a number of folks, and then we'll all be available for Q&A as well. With that, why don't we go ahead and dive in? So Kevin, why don't you take us to the next slide? Yeah, so just a little bit of the background of their study. We wanted to kind of relook at what the economic opportunities are for distributed wind energy systems. For those of you that may not be familiar with distributed wind systems, they really scale from kilowatt kind of residential applications up to megawatt scale community applications. And we were focused on two particular snapshots in time, 2022 and 2035. In the 2022 snapshot, we really focused on kind of business as usual current policy conditions, whereas in 2035, we looked at a number of scenarios to explore sort of the uncertainty that exists with respect to key parameters that we're modeling. What we really sought to achieve is an ability to kind of characterize and understand what the opportunity is for distributed wind to play in the energy transition, particularly as we're thinking about the levels of wind deployment that might be needed to serve a zero carbon economy out there in the 2035 and 2050 futures. Our basic approach was to use NREL's Djen modeling suite, within which we have our DWind model that looks at the economics for distributed wind energy systems. We used a new metric that we defined particularly for this study, which you'll hear a little bit more about later on in the presentation, but the threshold capital expenditures, or the threshold Capex, is sort of a key metric. We use the data and the models to understand the economic potential. So we define sort of benchmark costs that determined whether projects were economic or not, and use that to characterize economic potential. And then we really wanted to focus in on areas and particular locations where distributed wind was relatively more or less viable, identify those good opportunities for deployment, and inform the public and the user community of where those opportunities might lie. We also did want to look at sort of opportunities in disadvantaged communities across different land use types, agricultural, commercial, industrial, and residential land use, and then of course look at the opportunities for different turbine sizes too. Go ahead, next slide, Kevin. Just super quickly, I think many of you are pretty familiar with distributed wind technologies, but if you're not, we're really looking at two different types of distributed wind applications: behind the meter applications and front of the meter applications. Behind the meter is what you would maybe more traditionally associate with distributed energy solutions or distributed energy systems. This is an on-site generator that's directly offsetting retail electricity. Again, this can be from kilowatt to megawatt scale, depending on the local load that you're offsetting and what the user is doing with the electricity. We're mainly talking about rural or suburban homes, farms, and manufacturing facilities for behind the meter applications. Front of the meter applications, probably the easiest way to describe this is to think more about community scale energy, but specifically it's connected to the distribution network, and it's going to serve the local loads that are there on the distribution network. You may be placing these types of systems strategically to support the grid, to provide grid services or offset future grid upgrades. Yeah, the front of the meter applications tend to be much larger, hundreds of kilowatts and megawatts, and they may involve multiple turbines. So Kevin, go ahead, next slide. Yeah, so for those of you that aren't familiar with the Djen modeling suite, this is just kind of one example from some prior work that we did focused on a few states. In this example, we're looking at Colorado. This is a model that we use that looks at really detailed spatial data to identify what types of distributed generation might make sense for a given place in space. We have the ability to look at to integrate consumer decision-making processes into the analysis as well. We didn't actually consider consumer behavior in this particular study. We just looked at the economics. Consumer behavior is a whole nother area of research, and so that was outside of scope for us today. But we were looking at the many drivers that might enable siting of these facilities and then sizing them to the particular load of the location. And how it might interconnect with the grid and ultimately provide electricity. The tools from the Djen suite, including dwind, are open source tools available at the link there that's shown on the slide. Just in terms of explaining what you're looking at on the left-hand side of the slide, in terms of how the model works, we're ending up in panel A with sort of an economic potential characterization. We're using detailed, highly resolved wind resource data, which is shown in panel B. If you go directly down clockwise to panel D, this is a way we can characterize the siting potential of different turbines, so you can see where it's possible to put particular turbines or not, and you'll get to hear a little bit more about the parcel data set that underpins the model here in a few slides. And then we're also looking at, particularly for behind the meter applications, the local energy use for a given user type, and considering that in terms of what types of turbines, what size of turbines might be accessible for particularly those behind the meter applications. So I'm going to wrap up my portion here with just a few highlights on the key messages. Kevin, why don't you go to the next slide? And then I'm going to turn it over to Ashrita Prasanna, who's going to talk to you briefly about the methods, Kevin McCabe, who's going to take you through the detailed results, and Jane Lakshan, who's going to talk about the intersections with energy equity. I'll come back on at the end just to kind of wrap up with some of the key, more specific conclusions than what you see in the key messages here, and then we'll move into a Q&A session. So really at the very highest level, some of the key messages that came out of our study are that there's really quite a large quantity of economic potential from distributed wind applications today and in the future. We actually estimated over nearly 1,400 gigawatts of distributed wind energy capacity that you could profitably deploy today. And if you run the simple math on this, this is actually enough electricity to power more than half the nation's current annual electricity consumption. One of the things that we think about as we look to the future is that policy does play a really important role. This is perhaps not surprising to those of you that have been in the industry for a long time, but it was really stark in our study how big of an impact the policy has on the amount of economic potential, and of course on the technology's ability to compete with other distributed generation resources and other sources of wholesale bulk power as well. So what does this all mean? Basically, there appears to be a very robust opportunity for distributed wind, really of all sizes, kilowatt to megawatt scale, to supply rural homes, businesses, and communities with a local source of clean electricity to support their energy needs and future energy objectives, especially if they're interested in low carbon technologies. So those are some of the key messages. Without further ado, though, let me turn it over to Ashrita, who's going to talk a little bit more about the methods we use to do this study. So thanks so much, and take it away, Ashrita.
Thanks, Eric. So hello, everyone. My name is Ashrita Prasanna, and I'll talk through a little bit of the data and methodology we use in this analysis. Kevin, the next slide, please. So a novel aspect of this analysis was the use of parcel scale data, where a parcel is defined as a taxable plot of land. So the parcel data set that we use contains information about the land area, the land use type, and a number of other features. And by combining this data with other data sets, for example, a data set on building footprints, we were able to identify location-specific siting and resource characteristics. So here we use the parcel data set to calculate the technical potential as well as economic viability for distributed wind and distributed solar in both front of the meter and behind the meter configurations. So we sampled parcels from the parcel data set, which contains over 150 million parcels across the United States. And the figure on the right shows an example of parcels in a particular area and how you can zoom down into specific parcels and look at their characteristics. Next slide, please, Kevin. So yes, as I mentioned, this parcel level database, extremely informative, containing almost all of the parcels in the United States, was used in combination with a number of other data sets on building footprints, zoning, geography, to apply land exclusions, as well as identify siting for distributed wind and distributed solar. We also used the renewable energy potential model to obtain the location-specific hourly generation and capacity factors. We used Cambium, another data set or data source developed at NRA, using production cost and capacity expansion models. So we use the Cambium data to derive the value of produced electricity from participation in wholesale electricity markets, that is in the front of the meter configuration. And so we used the data to quantify the energy and capacity values, as well as long-run avoided emissions. And finally, we used the System Advisor model, also developed at NREL, to implement the technology and valuation calculations. Next slide, Kevin. Thanks. So here, this slide basically defines the workflow which we use once we sample parcels. So the first step from the over 155 million parcels, we downsampled 1 million parcels for each scenario. After we select these parcels, and we did that simply for ease of computation, we are in fact able to do sample as many as needed. So the next step was to size systems, that is both either distributed wind or ground mount or rooftop solar in the case of distributed solar, based on the specific characteristics of the parcels, that is the available land area, by applying land exclusions, by considering the building footprint. And that tiny image on the left shows an example parcel where a wind turbine is being sited. We then assess the resource potential using the renewable energy potential or the REV model to obtain the hourly 8760 generation and capacity factors. Finally, we're applying the valuation framework. So we have two options: the front of the meter valuation, where we consider the value of this resource or this generator participating on a wholesale electricity market, and behind the meter, where we're considering the case where this generator is offsetting the local demand of the customer, which is located at the parcel. So finally, the next step, the threshold Capex. We, by applying this valuation framework, we optimize to try to identify what would be the threshold Capex cost or the Capex cost of the system at which it would break even. So basically, threshold Capex costs that are higher indicate that it's easier for the system to break even if Capex costs are lower than that. But I'll go into that on the next slide. And the final step here is after we calculate threshold Capex for every sample parcel, we then go on to calculate technical and economic potential under all of the scenarios, as well as identifying different spatial trends depending on the scenarios. Next slide, please, Kevin. So here, I'll just briefly introduce the concept of this threshold Capex supply curve. So as I mentioned before, we sample 1 million parcels under each scenario. So here, this is an example on the right of a threshold Capex supply curve, where we have ranked all of the threshold Capex from highest to lowest and the associated capacity for each of these Capex values. Now, we use benchmark Capex values for specific to 2022, what we consider the current year, and 2035 to start to quantify the opportunity available or the economic potential. So assuming here a specific benchmark Capex of $4,000 per kilowatt, we can then intersect that with the threshold Capex supply curve and identify the economic potential under that curve. So basically any project or a manufacturer or supplier which can provide the technology at the Capex at or below that benchmark Capex value will be able to be profitable for at that benchmark Capex. And on the left are just some of the caveats of this threshold Capex supply curve, or what is considered or what isn't considered. And that brings me to the end of my description. Happy to answer more questions later, and I'll let Kevin go on to describing the results.
Yeah, thanks, Ashrita. And if it wasn't explicit, please feel free to place questions in the Q&A panel or within the chat, whatever's easiest, and we'll try to leave a good amount of time for discussion at the end as well. But I'll jump into, excuse me, some of the results and key figures. First, I want to frame the discussion by talking a little bit about our scenarios. For this study, we employed a scenario framework to analyze the sensitivities to single or in some cases multiple input parameters and better understand the impacts of these parameters on economic outputs. So this table just summarizes the 8 total scenarios that were investigated in the study. They break down broadly into 5 main categories of inputs: cost and performance, financing, a policy extension, which considers ITC, as well as market value or compensation levels for DERs, and then ease of siting. There's also one optimistic scenario that assumes support for distributed wind across multiple fronts by combining the most favorable assumptions from each of the other sensitivities that we're modeling. It's also important to note here that these scenarios reflect snapshots in time, as Eric was mentioning, snapshots in time based on specific conditions. So for this study, as Eric mentioned, we selected the years 2022 and 2035 as those 2 snapshots in time. This approach was in part taken due to manage high performance computational needs and the need to process and manage and disseminate these results and data. So, you know, all that taken into consideration, in addition to the sensitivities and optimistic scenario, our 2 baseline scenarios could be thought of as 2 slices from a common set of business as usual conditions that would normally vary through time, but we're just looking at single years. So the report itself has a primary focus on the baseline 2022 scenario, as we had hoped to investigate current conditions faced by the industry and the opportunities that exist. Though of course, we also analyzed the baseline 2035 results with similar fervor, as we had hoped to understand the business as usual case for industry conditions in that year. The results presented here will follow a similar pattern, as we hope to show primarily current and secondarily future opportunities for distributed wind in aggregate and across regions. So just jumping right in, this slide presents the aggregate supply curves for behind the meter opportunities specifically. Ashrita just presented a little bit more in depth on how to interpret this type of graphic, so I won't spend much more time, but this supply curve representation of results ranks each parcel from highest to lowest threshold Capex and identifies the total available distributed wind capacity for behind the meter applications. So this representation allows us to compare the broader results of the study at a national scale across multiple scenarios. And so again, of particular note is our selection of a benchmark Capex value, the estimated current market capital expenditure for value for behind the meter, and as you'll see later, for front of the meter applications. And so when combined with the supply curve, we can determine the amount of distributed wind capacity that is favorable relative to this value. and that is the amount, that capacity is the amount that we define as economic potential. And so for behind the meter in the baseline 2022 scenario, that benchmark value is shown here, $5,675 per kilowatt. The report has much more detail on this, so I won't go into much more there. But here we're just focusing on 4 specific scenarios from the study to facilitate better interpretability. And there's a variety of noteworthy outcomes here, just to summarize quickly. In particular, we see obviously the magnitude of these threshold capex values for behind the meter systems will be more apparent when comparing with front of the meter, but the magnitude is quite high and results in the vast opportunity of economic potential for behind the meter systems, even in our baseline 2022 case. The siting scenario, for example, would increase the technical potential that the black line, as shown there, increases the extent of that x-axis, the x-axis extent, but doesn't necessarily impact the threshold capex or economic values. Obviously, the primary benefit from that scenario was just to allow turbines to be placed in more locations, and therefore economic impacts were, not really a consideration there. Also, it's quite obvious that the optimistic scenario is much more favorable than the baseline scenario. And I'll get into a little bit of those details in the next slide, but the impact of policy scenarios, in addition to some of the other sensitivities, results in a much higher estimate of economic potential when comparing this supply curve to our benchmark capex value. So moving on, from a tabular perspective, we can see the aggregate directional impacts of each scenario relative to each of the baseline scenarios. And so we note here that the current amount of economic potential estimated for behind the meter systems in 2022 was approximately 919 gigawatts. So a pretty vast opportunity in the near term for behind the meter systems, behind the meter distributed wind systems. As we shift to the 2035 baseline scenario, we note a decrease in that economic potential, and that's primarily due to our modeled assumptions on things like policy expirations. We assume an expiration of small wind ITC, as well as expiration of state and utility specific net energy metering policies, which would affect behind the meter viability. And then looking at some of the other sensitivities relative to the baseline 2035 scenario, opportunities in that behind the meter space can increase due to things like, in the ITC scenario, for example, we extend that ITC, extend net metering policies, and we see a significant effect, nearly doubling of the 2035 total for favorable policies of that kind. And then, of course, in the optimistic case, combining all of the positive sensitivities results in even more estimated economic potential. So in the front of the meter case, we'll look at the supply curve representation again. Here noting again the use of our benchmark capex value, which in this case is of course different from what we're using for the behind the meter case. For our baseline 2022 scenario, we're using a value of $1,608 per kilowatt, which is similar to what would be seen for utility scale wind turbines, with some other considerations as well that the report details. But again, this allows us to view the aggregate national potential for various scenarios. And here it's a lot more apparent, especially with respect to the threshold capex values, the magnitude of values more like. We see that the front of the meter case has much lower threshold capex values, which indicate the need for these projects to be a lot more, have a lot more favorable conditions for economic potential to exist. And in this case, because we're also comparing against a smaller, a lower benchmark capex, we see different trends in what types of systems, what types of parcels are economic relative to that benchmark value. So looking at the tabular representation again, we note that there's in the 2022 near-term case, the baseline 2022 case, there's approximately 474 gigawatts of estimated, front of the meter potential, which again decreases as we look forward to the 2035 scenario, again, due to similar reasons for policy changes. In particular, we assume an expiration of the production tax credit, the PTC, as well as the ITC expiration as well. There's also modeled changes in terms of what the wholesale power market looks like, which can, be in either direction, but it does result in a change in values as we move through time. And then comparing the other scenarios, the other future scenarios to the baseline 2035, we see various changes as a result of changing these single variable, multivariable sensitivities. In particular, again, noting the ITC or the policy scenario being especially strong for the viability of the front of the meter market by extending the favorable policies like the PTC, the ITC. We see an order of magnitude change relative to the 2035, and then adding all of the positive sensitivities in the optimistic scenario results in an even bigger opportunity for the front of the meter space. So the parcel level data allows us to look at really granular spatial representations. And in this case, we're looking at continuing with front of the meter opportunities for wind. The baseline 2022 scenario, this was a sort of a heat map representation that we constructed as a result of the very granular data we had available to us. And this allows us to graph or chart map the threshold capex values for each of the applications in each scenario. So drawing your attention to the color bar, again, noting the scale of the front of the meter scenarios, we'll see that change as we go through time and across scenarios. But this gives us a sense, at the state and county level of the general areas of opportunity for front of the meter applications. And in this case, broadly, those areas of interest include regions like the Great Plains, Midwest, South Central. Perhaps it's not too surprising that areas of higher quality wind resource are primarily driven, the economic viability of these regions is driven by the higher quality resource for front of the meter applications. Because as has been mentioned, front of the meter systems are modeled as bidding into wholesale power markets. Stronger resource is going to result in much more viable systems. Though we also note that regions with high cost wholesale electricity can also return high threshold capex values, and therefore you'll see certain niche areas, the Rust Belt, the Northeast areas, there are pockets of front of the meter areas where that type of configuration can thrive. And then moving forward in time to the baseline 2035 scenario for front of the meter wind, there are very similar areas of economic viability. Those same regions, Great Plains, Midwest, South Central regions remain strong areas. Though again, looking at the scale of the threshold capex, the color bar there, we note a decrease in the general magnitude of those values, again, reflecting some of the expiration of certain policies, the sunsetting of some of these specific wind energy policies, such as the PTC and ITC, as well as the general changes in modeled wholesale prices that result as we move into the future. And then looking at near-term opportunities for behind the meter wind, the baseline 2022 scenario, it's quite apparent where some of the areas of interest are just relative to the rest of the country. Again, noting the scale change on the threshold capex color bar there. In this case, we're looking at very specific or states and general regions as areas of interest here. California and Minnesota in particular pop out as areas of interest, as well as the Northeast New England region as well, show high viability. And it comes as no surprise that good resource for behind the meter wind is something of a necessary but not sufficient condition for this viability. And we also note in the behind the meter case, regions that exhibit high retail electricity prices, as well as favorable policies, are also contributors to applications that have that exhibit profitability. So California in particular is of note there. And as we move to the 2035 baseline scenario, The scale remains somewhat similar, but the results, the spatial patterns are a little bit more diffuse between the 2022 and 2035 scenarios, though it's quite obvious that California remains an especially strong area of economic viability and an area that developers, stakeholders could potentially target as one for further investigation. But similar to the front of the meter case, the sunsetting of policies, in particular the investment tax credit ITC, which is particularly suitable for behind the meter applications, as well as expiration of net metering policies, also very specific to behind the meter configurations. Our modeled expiration of those policies results in generally lower threshold capex values, lower in magnitude relative to 2022. And so I'll wrap up with a few slides here on kind of sectoral opportunities. And as a result of the very detailed granular parcel level data used as a foundation for this study, we're able to break out the specific opportunity space for different general land use types and determine what this opportunity space looks like for sectors and subsectors of interest for distributed wind applications. Of particular interest, especially for wind and distributed wind applications, has historically been the agricultural sector. These agricultural land use types are widely used for large-scale wind power plants. So it's natural that opportunities for distributed wind energy applications are also significant in these locales. And so here we pull out all of the model results for agricultural land use types. So think, farms, rural parcels, things of that nature. And we were able to break down the results for a more specific subset of these outputs. And so one observation is that we observe a significant overlap between the national aggregate results and these agricultural specific opportunities, especially for front of the meter applications, as these agricultural parcels offer both high quality resource and abundant land. And within our modeling framework, we note that these agricultural land use types actually comprise the majority of the modeled parcels within the Midwest and Great Plains states. And so these graphics simply show the top 6 states for each distributed wind configuration behind the meter and front of the meter, which contain hundreds of gigawatts of economic potential for each of these applications. As I've touched on a little bit already, behind the meter systems, I and others have touched on, behind the meter systems are constrained by local load and are most correlated with a combination of where that electricity consumption is, the electricity rates in the prevailing area, and where windy land is, where good resource is. For front of the meter, again, resource quality and higher cost pricing nodes drives that profitability. The hope is that with these detailed county level heat maps that are also in the report, developers, stakeholders broadly can get a sense of where these sectoral opportunities exist and can concentrate efforts accordingly. So the opportunity within the commercial and industrial sector as a whole is smaller. That is reflected by the lower observed economic potential and the sparse spatial coverage within the maps. But nonetheless, commercial and industrial lands offer compelling near and long-term potential, particularly for behind the meter applications, albeit with a pretty major difference as compared to agricultural lands. We find that actually front of the meter applications are not typically compatible with sector needs, such as reduction in on-site load and demand and avoidance of electricity price volatility. Thus, we observe no measurable economic potential for front of the meter applications, and instead provide here and in the report a table that ranks states by threshold capex in order for stakeholders to better understand where opportunities might exist for front of the meter applications. But in the behind the meter case, we see that commercial industrial lands are broadly clustered around metro areas, which is also where we observe the greatest distributed wind opportunity for those configurations. In Colorado, Denver metro area, Kansas has Wichita, the KC metro area. Other correlations exist between metro areas and these specific states. But again, the opportunity as a whole is smaller, and you'll see that the in particular the white space shown in the maps reflects not only where the modeled CNI commercial and industrial parcels are, but the economics that result as well. And then finally, we identified the residential sector as one of particular interest within the distributed wind space, and broke out some of those sector-specific results here. Residential distributed wind energy provides landowners an alternative or complement to PV systems and can help counter especially high retail energy prices. And so policies like net metering, certain incentives like the ITC can make residential systems a cost-effective solutions. And so we find that economic potential on residential lands is driven by total area with favorable conditions. However, there are certain pockets of favorability that are correlated with pockets of high retail rates, especially in California and New England. And those are actually complements to the 6 states shown here, where behind the meter economic potential is largest. And so New York, the western part of New York, Buffalo, Rochester, Minnesota, the southwestern, southeastern parts of Minnesota in particular show good favorability. And again, similar to the agricultural and CNI, commercial and industrial outlook, developers and stakeholders can ideally, use these maps as areas of interest to target development or policy development, et cetera. The front of the meter opportunity space again is rather limited for residential parcels, since typical residential consumers would instead consider a behind the meter project. But similar to the commercial and industrial space, we observe no economic potential for front of the meter configurations, and instead here just provide specific rank data that point to those states and areas of interest. Though again, noting that perhaps front of the meter and residential sectoral opportunities might be seen as generally incompatible, but these opportunities could exist, and this ranked table shows where those broad regions might actually exist. A lot more detail in the report on these results. In addition, we have results broken down by turbine size, which we won't present here just for consideration of time. But please refer to the report for more detailed information on our modeled results. And also please feel free to drop some questions, and we'll be happy to address those in due time. So that actually does it from me, and I will turn things over to Jane to discuss the energy equity results.
Thank you, Kevin. My name is Jane Lakshan, and I am a geospatial data scientist here at NREL. And I will be presenting a brief overview of our energy equity analysis, where we explored opportunities for distributed wind energy in disadvantaged communities. Next slide, please. In our study, we defined disadvantaged communities as census areas with a high risk for environmental hazards and/or areas that include high proportions of low-income households. Exploring opportunities in disadvantaged communities is important because distributed wind has the potential to alleviate energy burden by lowering electricity costs, as well as bolster electricity reliability in these communities. Next slide, please. Thank you. Here are the results for the threshold Capex for front of the meter and distributed wind from our baseline 2022 scenario. We found that the states with the most economic potential in disadvantaged communities are Oklahoma, Illinois, Kansas, New Mexico, Nebraska, and Montana. Next slide, please. Thank you. Likewise, the baseline 2022 behind the meter threshold Capex values by state are presented here. It is important to note that this map was based off of threshold Capex values in disadvantaged communities, but for visualization purposes, the results presented in the map are not bound to disadvantaged communities. And for behind the meter, according to our results, the states with the most economic potential in disadvantaged communities are Texas, Montana, New Mexico, California, South Dakota, and Kansas. And this concludes my brief overview, and I will now hand the mic back to Eric for questions and discussion. Thank you.
Great, thanks, Jane. We've been trying to handle as many questions as possible in the chat thread live, and realize we offered you 2 places to post questions, the Q&A panel and the chat. So we're tracking both of those. Before we move into the full Q&A portion, just basically some of the key highlights and conclusions from the study to reiterate here. The first one is that the economics of distributed wind from a profitability perspective or an economic viability perspective are quite strong. That being said, there is significant competition from solar PV and other DERs, and as has been sort of maybe alluded to in some of the questions regarding interest in solar, it's quite possible that in some of these locations, even though they're profitable for distributed wind, solar PV would still provide an even higher return. We hope that future work can kind of better explore and elucidate those locations where distributed wind is particularly valuable, either as part of a hybrid system or even on a standalone basis, when the conditions are right and when there's policy parity to provide comparable economics or economic support from a policy perspective. Maybe that's a little bit of a segue to the second main conclusion here, that is, policy really does have a big impact on the relative economics. At one level, this is not surprising, but I think for me at least, the magnitude of impact was a little bit surprising, that it was the single largest factor, largely dwarfing all other variables that when we looked at on an individual basis in terms of the ability to open up additional areas to economic viability. So then that kind of re-raises this question of policy parity among the various DER technologies, and if there isn't policy parity, then one particular technology or another might be put at a significant disadvantage. Another key finding really is that the economic potential for behind the meter applications is actually higher than for front of the meter applications in the near term. But over time and under more favorable conditions, sort of the amount of available land that you could tap into by not limiting yourself to a specific on-site application, as is the case for front of the meter or more community scale applications. If the technology is cheap enough, then it becomes more a question of just the available land area, and so under the more favorable conditions over time, the front of the meter applications can come to exceed the behind the meter potential. Of course, as you've seen from the various maps, there really is a focus in terms of the potential on sort of the Midwest and Heartland regions. This is not surprising if you know the wind resource in the US and in North America more broadly. But I think particularly for behind the meter systems, it's really interesting to see some of the pockets that open up in areas where you have a combination of moderate to good wind resource, as well as the higher retail electricity rates and perhaps more favorable kind of net metering or net balancing type policies. Again, perhaps not surprising at the qualitative level, but pretty remarkable from the precise statistics. The agricultural lands are really a big chunk of where the potential sits. We're talking 70% for behind the meter applications, and approaching 100% of front of the meter economic potential is on ag lands. It's not quite 100%, 97% there to be specific, but a really big chunk is on ag land. So from a distributed perspective, if there's an opportunity to focus on a particular land use type, and you want the biggest opportunity, ag land is where that's going to be had. That said, sometimes in other sectors, commercial, industrial, for example, or otherwise, even though the overall aggregate opportunity looks smaller, there may be, it's still a sizable market, approaching a gigawatt in several states, particularly for behind the meter applications on commercial industrial lands in particular. So it's a big opportunity, and the economics might even be more compelling. So you kind of have to look at not only what's the size of the economic potential opportunity, but what's the relative threshold Capex that you can get for a given site, and do the due diligence there to differentiate those things. Yeah, it's just as a final conclusion here, it was interesting to us, to the research team, to see that there is significant opportunities really for all the different sizes of turbines. I think that you know, sometimes because of the relative cost differences that you can achieve for the larger turbines, the economies of scale that you can get from those turbines, and the efficiencies that come from being able to tap into the technology that is being developed by, you know, large multinational OEMs, that there's sort of a sense that the larger turbines might do better. But that's counterbalanced by the ability to offset retail rates that's perhaps a bit more abundant for the smaller turbines. And so, you know, that ability to offset those higher priced retail rates gives you a higher threshold Capex and a little bit more headroom. So even if your project's a little bit more expensive, it can handle that because of the ability to offset those retail rates. So there are good opportunities for all the different technology sizes. With that, why don't we go ahead and shift into full Q&A mode? And I know we've been trying to handle the questions through the chat. Let's see here. Yeah, there's one good question here that asks about, you know, access to the PowerPoint and to the data that's going to be associated with the published work. Maybe I could ask either Kevin or Ashrita to weigh in on access to the data. We do hope to publish these slides in the coming days, so they should be available via a public link probably within the week. But Kevin or Ashrita, one of you want to speak to the availability of the data?
Sure. Yeah, as Eric mentioned at the start, the distributed wind model is and the Djen model more broadly is actually open source, and we follow a timeline for open source releases targeting annually-ish. And so as a result of that process, we're hoping to release not only the latest version of this model, or rather incorporating developments from this model, but also hoping to release the data as potentially a data.gov submission. There are some considerations with how we release the specific parcel data, so we're working through some of that and hope to have some of the specific outputs from these scenarios released. And again, I believe we're targeting a more open access via data.gov.
Yeah, just to add to that, we are definitely interested in sharing the data. The parcel data itself has some confidentiality restrictions, so we will be aggregating the data up to county scale or on the best appropriate scale. That's just a caveat there.
Yep, perfect. Thank you both. There's another question here about you know, what we assumed for net metering or retail rate compensation going forward for behind the meter applications in particular. And I probably muddied the water there a little bit in terms of some of the overall high level remarks. But again, Kevin or Ashrita, one of you want to talk a little bit about how retail rate compensation evolved through time, given, you know, the relative dynamic nature of the policy discussions that are at play there.
Yeah. In our current understanding of net metering policies is reflected in that baseline 2022 scenario. So that's typically by state how we apply those policies, and that's you know, our best representation of full net energy metering where applicable, or, you know, net billing where applicable. But as we move into the future scenarios, the baseline 2035 scenario in particular, we actually assume expiration of most, if not all, of the full net energy metering policies. That's an assumption that we've applied in previous studies, as we don't understand what that landscape looks like, you know, 13 years from now. So we assume an expiration of those policies, and instead move to more of a net billing structure for most states. Retail rate compensation remains the same. We have a downloaded data set from the OpenEI's utility rate database, which gives us, you know, full representation of the retail rates as they exist today by utility, and include details such as, you know, time of use rates, demand charges, you know, fixed charges, et cetera. And so the compensation as a result of those avoided charges is really the driver, one of the primary drivers for behind the meter systems and their profitability. So I hope that answered the question. Happy to follow up if needed.
Yeah, I think that's great, Kevin. Thanks. I think the upshot is that you know, we do assume policy expiration, but there's still a relatively high value on the specific quantity of electricity that's offset. So maybe there's a lower value for any excess generation, but if you're still able to offset your retail consumption, then there should be some savings, relatively valuable savings there. But it is an uncertain space, and the question is certainly a fair one and one we wrestle with a lot. Yeah, there's several questions around sort of citing and the citing setbacks that we used. Ashrita, do you want to elaborate on that a little bit?
Yes, so I'll just respond again. So in the baseline scenarios, both the baseline 2022 and 2035, we had the setback factor of 1.1 times turbine tip height, and mentioned in the siting scenario where we consider relaxed siting, we have that reduced to 0.55 times turbine tip height. I know our commenter, Gordon Fisher, I think it is. No, sorry. Sorry, whoever the questionee was, wanted to see the impact of a higher setback factor. I mean, if you just look at our results, the setback factor does increase the technical potential, but it doesn't necessarily impact the economic potential there. So you might see some reduction there on the technical potential side, but the economics are kind of applicable, and you see that in our results as well. So that would be my comment, and yeah, that would be my response to that, but happy to have Kevin weigh in on that.
No, yeah, go ahead, Jane.
Or Jane, sorry, go ahead, Jane.
Yeah, I can add a bit to that. So during the citing sensitivity analysis where we were exploring different setbacks, we did not consider any that were higher than the baseline 1.15, or yeah, baseline 1.1 times the turbine height. And that was basically due to some research in what are the current setback restrictions for areas in the country that do have that identified, and then also some feedback from our technical review committee telling us, suggesting that we should reduce the setback to see what we could build if those, what our results would look like if we had smaller setbacks in specifically residential areas.
Maybe just another question for you, Jane, and this one it shows up as maybe a little bit technical, but I think really the question is, were we also accounting for less windy sites? And I think this is a reflection of our sampling methods. The short answer is yes, we include basically all sites, but I think maybe we have a little bit more of a weighting on, you know, moderate to windy sites. But Jane, do you want to speak to that a little bit more, or anybody else?
Yes, and this is not related to setbacks, correct?
Correct. Yeah, sorry.
Okay,
Shifting gears.
Just confirming. Right. So no, we did not sample the parcels based off of resource, if that's the question in particular. So we did identify the resource potential once we have once we've sampled the parcels for the model runs.
Yeah, so the sampling
the other reason,
go ahead.
The less windy sites, there is that correlation simply because as we walk through that process, so we sample, we identify resource, we do the valuation, and when the valuation there at that step, if the site isn't able to break even, we're not able to find any threshold capex. I mean, there's no identifiable Capex cost above 0, then that site is dropped out. So we can't show any threshold Capex below 0 are not reflected in our results. Those are just white, So that is why those sites are not showing up.
Here's one that just came in at the bottom of the chat thread. Is there an opportunity to take this research and apply achievable potential similar to work done for energy efficiency? Maybe I'll just take a quick crack at that one. I think the short answer is yes. I think we use the term more of market potential. There's 2 dimensions to that, though, that are somewhat analytically challenging, which is why they were outside of scope for this study. One is the competition between wind and solar, and then the other one is, I alluded to this earlier, but around consumer behavior. When we do market potential studies, we've done them in DWind in the past, and they do them certainly more broadly in the Djen suite. It's really around the consumer behavior question, which is at least in part, affected by some of the relative economics. For us, I think the future work would really be to do more head-to-head comparison with solar PV and with hybrid solutions to understand, again, where are those sites where wind has a particularly strong advantage? What are the conditions under which those advantages, shift the economics towards wind, or vice versa from wind to solar, and to not necessarily tackle so much of the consumer behavior question, just because that's one that would take a lot of effort to really elucidate. But we don't have a huge sample size also for people that are buying distributed wind systems at present. So until the market becomes a little bit more robust, I think we'll focus on the head-to-head comparisons and trying to suss those out with more detail. Oh gosh, we had a whole bunch of questions come here all of a sudden. I think we'll try and get them here in the last couple of minutes, but want to respect your time. So one question here, shouldn't reducing setback always increase economic potential because there will be more sites with the same economics? I think the answer is maybe. It depends a little bit on precisely how you're computing your potentials and how much you want to sort of allow for very, very proximate turbine siting. So there are some sort of details in the way you do the math that can affect exactly how the economic potential challenges come out. One of the things that we did in these numbers actually is put a limit on the turbine densities that you could achieve of 3 megawatts per square kilometer, based on typical turbine densities from wind farms that are in arrayed locations. And so some of those factors can sort of result in a little bit of sort of muting of some of the effects, particularly for the behind the meter systems. So we did kind of have a muted effect there. Yeah, and I guess there's a similar question. Go ahead, Ashrita.
Just to add again, I think Jane's answer is the more accurate one, because I wasn't sure what stark differences you were referring to. But yes, that is because, as Kevin mentioned and as Jane has mentioned, those are state level policies on net metering that expire or don't expire in future years. So that is why you see differences across state lines. Aside from that, in the coloration, those differences are just reflecting the threshold Capex cost for a specific sample site. I'm sorry, back to you, Eric.
Yeah, no worries. Yep, no. So that was jumping back to the question around some of the border differences that you see within the maps. And yeah, I agree that the net metering policy there is a pretty significant component of it. There's a question from Josh about the potential for relaxed siting, particularly for front of the meter between in the 2035 scenario. I think that's one actually that we need to dig into a little bit more. We noticed that as well as we were kind of crunching through the final numbers, but it got stuck a little bit maybe maybe in the cracks in the cutting room table. So that's one that we should dig into and follow up with you on. And pretty sure there's a sort of a underlying explanation for it, but we'll circle back with you there. Yeah, I think that's most of the questions. Hopefully we got through everything. We are at 1 minute past the top of the hour. Yeah, there was the question on the Capex, and I think Perrin got back with a thorough response there. I think that the only thing I'll add to this, because it ties in with the permitting side of things, is that one of the reasons we went with the threshold Capex approach is because there's a fair bit of uncertainty in what actual project Capex could or might be, whether that's a function of differences in turbine pricing or the unique characteristics of a particular parcel. And so the threshold Capex, it's more of an indicator of how much can you spend and still make money at this site. And so if you have to do a lot of sort of supplemental infrastructure upgrades, or build a long line to interconnect the system, as long as you can do all of that, or if you have to spend a lot of money on the permitting process, as long as you can do all of that at some value that's below the threshold Capex, then you're still in the black. But if you have to do those things and they push you above the threshold Capex, then you're going to be in the red on the project. So we didn't address those things explicitly, but I do think that the analysis can still provide some insights on that front. Any final comments from the panelists, or any questions that you might have seen that I missed? All right, well, with that, thank you all for your participation and attendance of the webinar today. I should have said it at the outset, but I think we also want to extend our gratitude and thanks to our DOE sponsors, in particular, Brett Barker and Patrick Gilman, who I believe were on the line earlier. Not sure if you still are or not, but thanks to DOE for supporting this work and bringing it to fruition. We look forward to getting the data out as part of that open source model release that Kevin described earlier, and we'll tie off that question as well around the front of the meter economic potential and the siting dynamics there. So thank you all so much for your time. And until the next Distributed Wind webinar comes along, wish you all the best. Take care, everybody. Bye-bye.
Thanks, everyone.